Here are solutions to homework set number 5 for ECE 341, Random Processes. This homework looks at geometric and Pascal distributions. The first problem is, suppose I have an 8-sided die and I keep rolling it until I get a 1. Determine the PDF of A using Z transforms. And from this, compute the probability that A is equal to 10 and A is greater than 10. The Z transform would be 7/8 of a chance that I fail, 1/8 chance of success. So this is the Z transform. To take the inverse Z transform, I'll multiply both sides by Z. That's put this in a form that's in my table. That becomes 1/8 times 7/8 to the k U of k. Now divide by Z, and that's a time shift. 1/8 times 7/8 to the k minus 1 U of k minus 1. So there's the PDF of a geometric distribution. Roll an 8-sided die until I get a 1. In MATLAB, if I take this out to 200, that would just be 1/8 times 7/8 to the k minus 1. And I've got to use the dot notation. That tells MATLAB, treat this as element by element operations, not matrix. When I add them all up, the sum of A is 1, meaning it's a valid PDF. A of 10 is the probability of it taking 10 rolls. That's 0.0376. And the probability it takes more than 10 would be 0.3007. I'm sure to go out to infinity. I just stopped at 200. Problem 2 is use a Monte Carlo simulation with 100,000 A's. And repeat. So here's what the code looks like. I'm going to start out with 0 events. I'm going to repeat 100,000 times, starting at 1. I'll keep on rolling the dice until I get an A1 on an 8-sided die, or as long as the probability is bigger than 1/8, keep rolling. As soon as it's less than 1/8, I kick out. When I do that, n is the number of rolls it took. Add 1 to that counter and repeat. Repeat 100,000 times. When I do that, it took 10 rolls, 38,003. It took 10 or more rolls, 30,037. Divide by 100,000. That gives you 3.8% versus 3.76 computed. 10 or more is 30.3% from a Monte Carlo. Should be 30.07. So again, that seems pretty consistent. Problem 3 is a Pascal distribution. Suppose I roll an 8-sided die until I get a 1, and then I roll an 8-sided die until I get a 1 or a 2. X is the total number of times I roll the dice. What is the PDF of X? Find that using Z transforms. Well, for A, here's the Z transform of A. Here's the Z transform of B. A, there is a 1 in 8 chance of a success. In B, there is a 2 in 8, or 1 in 4 chance of success. The convolution of the two is the multiplication in the z-plane. Now take the inverse Z transform. The trick I'm going to use is multiply both sides by Z, do a partial fraction expansion, multiply 3 by Z, take the inverse Z transform. So this is 0.25 times 7/8 to the k, minus 0.25 times 3/4 to the k. Then divide by Z, meaning doing a time shift. So here's the PDF of A plus B. In MATLAB, I can do that. Let's just go out to 200. 200 is an arbitrarily large number. Here's x of k. If I find out what is x of 20, there's a 1.87% chance the total number of die rolls is 20. Add them all up between 20 and infinity, or in my case, 20 to 200. 15.4% chance it's going to take 20 or more rolls. And the sum of all rolls is 1. That's just kind of a check. Is 200 far enough? If it's less than 1, I miss some of the tail. Problem number 4 is repeat using convolution. So let's again go out to 200. This is the PDF of A. It's 1/8 times P times Q to the K minus 1 for k greater than 0. B is P times Q to the K minus 1, K greater than 0. And then to do the convolution of A and B, just do convolution of A and B. And I'm going to truncate it to 201 spaces, so it matches up with K. Add them all up, I get 1. So this is a valid PDF, which means, in theory, this goes out to infinity. At some point I have to truncate it. Is the part that I truncate is significant? At least to 4 decimal places, it's not. The probability that it takes 20 die rolls is x of 21. Again, everything's offset by 1. 1 means 0, 2 means 1. 1.87% chance, same thing I got with Z transforms. The area of 20 or more is 0.154, same as Z transforms. So convolution is another way to get the same answer. Problem 5 is do a Monte Carlo simulation, a third way to solve. So here what I'm going to do is I'm going to keep rolling an 8-sided die until I get a 1, keep rolling a 4-sided die, or 8-sided die getting 1 or 2, until I get a 1. Add up the number of die rolls and increment a counter. Repeat 100,000 times. That's the Monte Carlo simulation. With the Monte Carlo, it took 20 rolls 1.88% of the time, supposed to be 1.87. It took 20 or more rolls 15.3% of the time, supposed to be 15.4. So again, the Monte Carlo again confirms what I just did. Problem number 6. This is roll an 8-sided die till I get a 1, until I get a 1 or a 2, 1, 2, or 3. Count the total number of dice times I roll the dice. That's a Pascal distribution, in which case the Z transform is probably the easiest way to do it. Take the Z transform of A, B, and C, multiply them all together. That's the Z transform of Y. To take the inverse Z transform, again multiply by Z, do partial fractions, multiply through by Z, take the inverse Z transform, delay by 1. Okay, there is the PDF for A plus B plus C. In MATLAB, if I plug in numbers, I can sit there and say that the total probability is 1. It's a valid PDF. The probability of it taking 20 die rolls is 2.65%. Probability of 20 or more rolls, 22.47% chance. Let's check that answer. Problem 7 is repeat using convolution. So here's the PDF of A going out to 200, B and C, convolve A and B, take that result, convolve it with C. Here's a convolution of A, B, and C. Truncate it to 201 spots to match up with K. Check to see this is a valid PDF, meaning the part that I truncated is not significant. Probability of 20 rolls is the same that I calculated. Probability of 20 or more rolls, same that I calculated. And finally, using Monte Carlo, I can do the same thing. 20 rolls is 2668 out of 100,000, which is 2.668% versus 2.65. 20 or more, 22.39%, 22.47%. Again, Monte Carlo again confirms those numbers. So with geometric and Pascal distributions, there's a couple ways to solve. I can use the Z transform. This gives me an explicit equation for the PDF. I can use convolution. That doesn't give me an explicit equation, it just gives me numbers that I can use in MATLAB. I can also use the Monte Carlo simulation. Monte Carlo answers won't be exact, but they'll be close. And that's homework set number 5 for ECE 341.